All right, so we get started today. Going to begin with a review exercise, practice exercise number 84. Practice exercise 84, you may use a calculator for this exercise. And one thing that you might remember going back in your minds to your junior high days is something called perimeter. Okay, so rectangle, perimeter, remember a rectangle has two lengths or bases and two altitudes or heights or widths. So to find the perimeter of a rectangle, just double the length, double the width, and add them together. To find the perimeter of a square, since a square has 4 equal sides, you just add the 4 sides together, or better yet, multiply the side's length by 4. What we're going to be, before we get started, Ethan, what we're going to be working on over the next large part, actually, is transitioning out of just an algebra focus into a, we don't want you to forget all of your junior high geometry. So a lot of junior high level geometry stuff coming up in the next set of exercises. Exercise 84, as we go into the fourth quarter, go ahead and get started.
Please calculator.
I already said you may.
Oh, sorry.
All right, let's go ahead and take a look at these together. And Chris was first. Chris, going across the top row, we had a rectangle that was 19 feet by 7 feet. What's the perimeter?
52 feet.
52 feet. Good. We had a square that had a side of 9 inches. What's the perimeter?
36 inches.
36 inches. And a square with sides of 4.3 feet.
17.2 feet.
Excellent job. Next row, going across, we had a rectangle that was 11 inches by 9.5 inches.
41 inches.
41 inches perimeter. A rectangle that was 5 feet by 15 inches.
40 feet.
Oh, it tricked you. It got you. Ethan, are you good on the first 4?
It got me.
It got you as well. Kendall, it got you too? Okay, let's go to the last one and then we'll come back to this one. Chris, what did you get for the perimeter of that last square that was 2 2/3 inches on each side?
10 2/3 inches.
10 2/3 inches. What do we have to do on that last rectangle? Convert something, right? Either make 15 inches into feet, which I don't like. What would that be, 1 1/4 feet? Or make the 5 feet into 60 inches, right? And call it out when you've got it. Let me do that real quick.
150.
150 inches would have been our answer there. All right, well, we came close to some candy. That one gets them every year. It's just a sneaky little... I know, you're not paying attention, right? But those units matter, don't they? As we saw when we talked about ratios in this class, units have to match. And here units had to match. All right, let me go and collect those from you. And go ahead and just about a piece of paper. We're going to do some practice here with some pictures and proportions. I want to start by reviewing over some past pictures and proportions, but then really want to spend some time focusing on that very involved picture that we looked at in yesterday's lesson, Theorem 61's picture. But first, I want to review very quickly some different things. So if I were to have a picture that involved a triangle, and I were to bisect one of the angles. Now again, this looks kind of isosceles-ish, but we can't trust our eyes. We just are given there's an angle bisected. On your paper, if you would, write the proportion in, let me give you letters. Let me give you letters, actually. Let's call this W, X, Y, Z. In letters, what proportion? Now think words first, then write letters. What proportion goes with a picture involving an angle bisector? write it down.
Okay, yeah.
I'm writing it down on your paper. Number 2. If I have 2 lines that are given to be parallel, and from point P, I've got 3 transversals drawn, intersecting these parallels at A, B, C, D, E, and G. What proportion can we set up based on this picture? I think Audrey's getting immune. She didn't even flinch. It's no fun to pick on Audrey now. All right, for the next picture, I've got 3 parallel lines. I've got 2 transversals, and these points intersect at J, K, L, M, and O. What proportion can we write based on this picture? Again, those letters represent points of intersection, since they are capital letters. All right, Brecken, if you would go ahead and set that aside. How about just a pen? How about just a pen? Please, when you're finished, you would set it on the cart. I'll come by and get it. The next picture, I've got a triangle. And one side of the triangle has been extended to form an exterior angle, which is then bisected. This side is extended out here to meet the bisector. Let's call this triangle A, B, C. We'll call the extension to D, and we'll call this point down here P. What proportion can we write based on that picture? Again, imagine, ooh, that's really bad. I say imagine straight lines, but a little bit much on the imagination. Now it's going up, whatever. An artist I ain't.
You ain't.
I ain't. All right, write the proportion based on that picture. We have an exterior angle now being bisected. For the next picture, we've got a triangle which we'll call QRS, and we've got a line, let's go like this, parallel to RS, and we'll call it TU. There are actually 3 proportions based on this picture. Give me all 3. We've got a parallel line, TU, drawn parallel to SR. 3 proportions based on this picture. Give me all 3 proportions. All right, I want to pause here before we look at the picture that we looked at yesterday. We're going to drill over that in just a moment. But for now, let's see how well we remember the old pictures. Anytime there's an angle bisector in a triangle class, the proportion in words is segment is to segment is side is to side. So we're going to say, well, what are 2 segments that have been formed, Kendall?
YZ and ZW.
Right, YZ and ZW. Segment is to segment as, what are the other sides then, Kendall?
XY and XW.
Good, XY and XW. Again, the alphabetical order may be somewhat haphazard here, but right, segment is to segment as side is to side. And it does have to be, if you start with the top segment, you have to go with the top side, bottom segment, then bottom sides as the consequence. Did we have this proportion? Excellent. Coming to this one, this was Theorem 60's picture. I've got 2 parallels. I've got multiple transversals cutting the parallels at points A, B, C, D, E, and G. Audrey, what proportion could we write based on this? Okay, so yeah, so A isn't a piece, A is a point, B is a point, so AB would be a piece. Does that make sense? Capital letters represent points. A is this dot right there. That's all A is. B is this dot, so if you're meaning this piece here, this is called AB. So AB is to there we go. Good. Piece is to piece, as piece is to piece, that correspond to each other. So we have this here. Okay, does that make sense, by the way? Again, if I could just call this like M, lowercase n, R, and Q. Lowercase letters can represent segments or two capital letters. So let's go with the double capitals here. What about, wait, everything's consistent, just everything's capital letters. Look at the next one, Chris. I've got multiple parallels this time and just two transversals. What proportion could be right?
M is to N.
Well, M is a point,
Yeah.
N is a point. You cannot compare points, you can only compare segments.
Mn is the JK.
Okay?
As KL is to N.
Uh-oh. If you're going to start with this transversal, stay starting with that transversal. So you said Mn over here is to JK over here. We need to start over here again.
As NO is to KL.
There we go. Does that make sense? So this piece is to that piece as this piece is to that piece. Basically the same thing. It's just one has multiple transversals, two parallels. One has multiple parallels, two transversals. Now I normally would start here and say JK is to MN is to KL is to NO. It's the same thing. Doesn't matter which side you start with. Question, Ethan, your face says question.
J is to M and K is to N and L is to O.
I'm sorry?
I had J is to L.
Okay, but again, J is a point. You can't compare points to each other. Points are infinitely small. Segments. Now, if I call this J, and I call this K, and I call this M, and I call this N, lowercase, I could say J is to M, but I didn't name it that. I called it JK. Does that make sense? All right, questions on that? All right, let's go to the next one. Ethan, I have another angle bisector. This time it's an exterior angle being bisected, but anytime there's an angle bisector in words, right, so what side got divided into segments?
BB. No. Yes. BB.
Here's my triangle. What side got chopped into pieces?
AB.
AB. And AB got divided into what two parts?
AB.
Is to
AB. No, BB.
BP. There we go. It's externally divided out here at P, but AB is the side that got divided into two parts. AP and BP are your two parts. So AP is to BP, segment is to segment as, side is to side.
BC.
If we start at A for my first segment, I need to start at A for my first side. So segment is to segment as side
AC.
is to
BC.
BC. There we go. Questions on that? How many have that? All right, questions there. And then coming over here, there are three different proportions in words I can use, but in letters, give me one of the ones you had, Kendall.
TS is to QT, SUR is to QQ.
All right, TS is to QT, bottom is to top. If you're looking at this as the base of the triangle, kind of mentally rotate it. Bottom is to top, bottom is to top. All right, and if you were to look at just at the means, you are cutie. Anyway, just the way the letters worked out. It struck me as you say, because you say QT and right after that you are. Anyway, questions on that? All right, we got another one though. What's another proportion we could use here? Chris?
I said ST is to UR.
Ooh, that is not correct.
TS is to UR.
Yeah, that is not correct. Audrey?
QS is to QT,
As QR is to QU. So you said the whole is to the top, as the whole is to the top. That is correct. So we've got bottom is to top as bottom is to top. We've got whole is to top as whole is to top. We need one more, Ethan.
So QS is to TS.
Whole is to bottom as?
QR is to UR.
There we go, whole is to bottom. There we go. Makes sense there. All right, questions on this? Now again, some of these were oriented a little differently. Instead of the vertex angle, I bisected a base angle. I bisected on the other side of what I normally did. I didn't make the parallel to the base. Instead of naming these just with single letters, I used double letter naming. Okay, so I changed it up to the way it's going to look just a little bit so that no matter how it looks, you're ready for it. Does this make sense? All right, now yesterday we added another picture. And we started yesterday with a right triangle. And what did we draw in the right triangle, Chris?
An altitude.
An altitude. Specifically, we drew the altitude from the
Bisector?
help him, Ethan.
Oh, the vertical.
From the right angle, and we drew the altitude from the right angle, obviously then class to the hypotenuse. So if we were looking at it in our standard orientation, where we're used to seeing the right angle down here in the bottom, we would draw from here straight across perpendicular to the hypotenuse. However, generally when we see the picture, we've rotated it, imagine that's a perfect right angle, so that the altitude comes down this way. Doesn't really matter what orientation you have. The point is that the altitude has divided the hypotenuse into two segments. We call it segment 1, segment 2. And of course there are two legs to the right triangle. Now notice, if this is segment 1 that attaches here, this has to be leg 1, so that leg 1 and segment 1 both come off the same point. Segment 2 and leg 2 then would also come off the same point. And we have three proportions based on this picture because we have three triangles in the picture, all of which, class, are similar to each other. We have three similar triangles, so we have three proportions. All of them have a mean proportional. Audrey, what does a mean proportional mean again? Second and third terms are the same. The means are equal. So in words, can one of you remember one of the proportions from yesterday?
The two triangles formed are similar.
That wasn't a proportion. We have three similar triangles. We already mentioned that, but I'm looking for a couple of proportions in words.
Leg is to segment is leg is to segment.
All right. Let's review first. We have segment is to altitude as altitude is to segment, meaning the two segments. So one segment is to the altitude is the other segment. The altitude is a mean proportional. Say that with me, class. Segment is to altitude as altitude is to segment. Again, segment is to altitude as altitude is to segment. A little bit louder. I couldn't hear Quentin or Genesis or Jamie, so need to hear you guys as well. A little bit louder here, class. Segment is to altitude as altitude is to segment. All right, and we had another one though as well, another mean proportional. And we want to take a shot at the other now that we've reviewed this one.
Would it be hypotenuse or altitude is to hypotenuse?
All right, here we go. It's segment is to leg as leg is to hypotenuse, where it's whichever segment with its own leg. So segment is to leg as the leg is to the hypotenuse, or segment is to leg as leg is to the whole hypotenuse. Say that with me, class. Segment is to leg as leg is to hypotenuse. Again, segment is to leg as leg is to hypotenuse. Quentin, Jamie, Genesis, make sure you're saying it with us. Segment is to leg as leg is to hypotenuse. So, let me take this triangle now. We're going to orient it a little bit differently. I'm going to call the triangle V never gets used. E very rarely gets used. F almost never gets used. And H. Okay, so let's go with these. V, E, F is my triangle. We've got V or FH, the altitude. In letters, what are the three proportions? Write them down. In letters, what are the three proportions? Again, there are technically two of these. They're both the same in words, segment is to leg is to hypotenuse, but there's two different ways to write that because there's two different segments and two different legs. Looks like Chris has them. Audrey's making an edit. All right, people finishing up here. Chris, what was your first proportion that you wrote down?
VH is to FH as FH is to HE.
Perfect. Segment is to altitude as altitude is to the other segment. Audrey, you were done next. What was one of the proportions you wrote?
VH is to
Good. This segment is to its adjacent leg as the adjacent leg is to the hypotenuse. And then what about the last one, Kendall?
HE is to EF as EF is to VE.
Sorry, I thought I heard you say VF for a minute. There's like realized no, you said EF. Okay. HE is to EF. EF is to
VE.
VE. Good. Segment is to leg as leg is to hypotenuse. So 3 different proportions there. All right. Questions on these different pictures and proportions. Let's practice with this guy right here. We're going to change up the lettering just a little bit now, though. So maybe on the back side of the paper that you were just using, go ahead and draw a picture, and maybe as I give you these lengths, lightly pencil them in. Because I want you just to use the same picture over and over, but it's easier to erase if you lightly pencil in. So start, if you would, by drawing to the best of your ability a right triangle. The best way to do it is start by making a right angle, and then connect the bottom ends thereof. We're going to call our triangle ABC, so that the right angle is at the vertex C. By the way, this is customary labeling for a right triangle to call the right angle C and the acute angles A and B. That's standard procedure. If you would go and draw an altitude straight down, and we'll call this CX. Using the proportions we just practiced with, if I gave you that AB was 10 and AX was 3, let's find CX. If AB is 10 and AX is 3, let's find CX. All right, before you can find CX, which is the altitude, you need something else, because the only proportion the altitude appears in is, say it with me, class, segment is to altitude as altitude is to segment. Well, here I see a segment. I'm finding the altitude as altitude is to, I don't have the other segment. Then it's easy enough to get, class. Must be 7, right? So, if we were to plug in the numbers now, Ethan, we would write
3 is to X as X is to 7.
right, and when we cross multiply and solve, we end up getting that CX is equal to, doesn't come out evenly, but it is, okay, let's cross multiply,
X squared equals 21.
and then what do we do to get X by itself?
I got stuck here.
Take the square root. It's the square root of 21. Which is like 4.6-ish, but I don't really care about the decimal. We're just going to leave what we call the exact value, which is the square root of 21.
Okay.
How many have the square root of 21 here? All right, now let's find some more things. Now that we know that the altitude is the square root of 21, we can use this to help us find, potentially, AC. Or maybe we don't actually need it to find AC at your seats. Bless you. in class, AC is what type of line? A leg. So we need a proportion that says segment is to leg as leg is to hypotenuse. How do I plug in the numbers here with that, Genesis?
3 is to x is to 10.
Right, and we know we're going to cross multiply, and then we're going to have to take a square root. What are we going to get for the length of AC? Square root of 30. How many have the square root of 30 for AC? Questions on that? Again, numerically that would be about 5.4-ish. But again, we don't care about the decimal. We're going to leave that radical value. How about finally BC? Let's find this length. BC. And once again, we're finding a leg. So once again, we need the proportion. Segment is to leg as to hypotenuse. Chris, this time, how do we plug in the values?
3.
What segment is up against the leg we're finding?
7.
7. So we need to say 7 is to
X.
x as is to 10. Segment is to leg is to hypotenuse. And what do we get for our BC? Square root of 70, which again would be about 8.3, 8.4, something like that. But again, we don't care about the decimal. We're just going to leave the radical value. Questions on this? All right, now let's go through and lightly erase all the stuff we've marked on the picture. So again, I told you lightly write it in. Go ahead and erase it. If you need to draw a new picture, there's nothing wrong with that, obviously. I'm just lazy. I don't know, maybe easier to just redraw the picture than it is to erase everything. This time, we're given that AX is 3, BX is 5. I want you to find AC, BC, and CX. This time, do all 3 at your seats. Always think, what am I finding? What proportion has that in it? Let me plug in the values. Check your first answer, AC, before we get too far into this. Did you get 2 times the square root of 6? You're finding a leg. Segment is to leg is to hypotenuse. Well, we weren't given the hypotenuse, were we? But if the pieces are 3 and 5, obviously the whole thing would be 8. How many found the hypotenuse to be 8? How many then set up the proportion that 3 is to x as x is to 8? And when you do, you're going to get the square root of 24. Now, unlike square root of 21, square root of 30, and square root of 70, this can be reduced. And just like we always reduce fractions, we always reduce radicals. So quick refresher in reducing radicals, factor the 24 into 4 times 6. Remember, you want one of the factors to be a square. Maybe a 4, a 9, a 16, a 25, a 36, a 49, an 81, a 64, an 81, a 100, a 121, a 144, a 160. Well, in other words, you get the idea, right? Thinking back to all the squares and stuff you memorized in your algebra class, Well, in this case, 4 is the easy one. 4 times 6 to get 2 times the square root of 6. On that note, find BC. On that note, find BC. Yes, sir.
Spencer's.
You call mom or you go to sleep? Right, Jamie, you want to watch the first half hour or so of the video lesson. I'm going to email it to parents. How do I set up my proportion this time, Audrey?
5 is to x is 2.
And 5 is to x, or I'm going to write BC as BC is to 8. So we end up getting initially BC is the square root of, initially, 40, right? 5 times 8 is 40, right? And then we need to see, can we factor in? And this is the reducing step. This is where the algebra kicks back in. What square is in 40? 4. So we're going to rewrite this now as 4 times 10, and we're going to reduce it down to 2 times the square root of 10. How many had that for the BC? How many have already solved CX? We've already solved CX. A couple of you. What is CX, obviously? Genesis?
Square root of 15.
Oh, wow. Okay. I was actually just looking for you to say altitude.
Oh.
But you're in your mind, you're already like, well, since it's the altitude, segment is to altitude, altitude is segment, obviously that's 3 is to x is to 5. And so that's going to be the square root of 15 for our altitude, and you are correct. Great job on that, Genesis. All right, did the rest of you who worked ahead also get square root of 15? We at least understand what Genesis did here. All right, show off. Same picture, same picture. You can either redraw it or just erase your given information. And this time, same picture. But we are told, beginning off, that CX is 6 inches. We are told that BX is 9 inches. We are asked to find AX, AC, and BC.
say? Just have to try and wait till lunch.
Questions on the initial step here? Getting that first piece AX, and therefore getting the hypotenuse 13. How many good to go on that initial step? Hopefully a little ahead of me. Questions at all on the first step? Go and pick it up from here if you can. Once you've got a x and a b, you have a segment and you have the hypotenuse, so you can do segment is to leg is to hypotenuse. How many got AC to be 2 times the square root of 13 inches? All right, questions getting that.
I did it now.
Got it now?
Before I didn't know what I was doing, but I figured it out.
Okay, you got it? All right, find BC then.
I already know.
Oh, you got it now?
Yeah.
Okay, all right.
I figured it out though, because I didn't know what I was doing before.
And when it comes to finding BC, again, you're going to do the same thing. Segment is to leg is to hypotenuse. Notice I didn't even waste my time multiplying 9 times 13. Because one of those is already a square. I'm just going to factor it back into 9 times 13 anyway, right? So why waste my time? I am that lazy. 3 times the square root of 13 inches for BC. How many had that for the last one? Questions on this picture? Do we feel like we start to know how to navigate the picture, solve for various pieces and parts? Let me give you one more of these and then we will move on. Same picture. Different given information. So I need to redraw the picture or just erase, as I am, the labeling on said picture. All right. Last time through. Here's what we know. We're given that AC is 6 feet. We're given that BX is 9 feet. And I'm trying to find AX, then CX, then BC. By the way, a quick note, find these in the order that I give them. Find these in the order that I give them. There's a reason for the order. And trying to find it out of order will cause consternation. Okay, so find them in the correct order. In words, what proportion do we want to start with? Anyone?
Segment is
See the altitude, segment.
Problem is, I don't know the segment,
Yeah.
and I don't know the altitude. I don't know the altitude is, I know this segment. That's going to be a hard one to use if there's 3 out of 4 things I don't know. The only other choice, though, would be, which I don't know the segment and I don't know the hypotenuse. But if I've called the segment X, then I do know the hypotenuse. Class? X plus 9. And now we can solve it. So use segment is to leg as leg is to hypotenuse. Did we set it up? X is to 6 is to X plus 9? And when we cross multiply, we get a complete quadratic equation set equal to 0 on the chalkboard. What do we do after we set an equation equal to 0?
Just move the 36 over as a positive.
No, we moved it over here to set it equal to 0. What do we do with a quadratic equation? Set it equal to 0 and
Factor.
factor. Yeah, there we go. Finish from here. Told you the algebra's coming back now. Remember, signs have to be different because of the negative. How do we split up that 36?
6 and 6.
Well, 6 and 6, outer inner would give you 0, not 9. 4 and 9 would give you 5 or negative 5.
8 and 4.
8 and 4 gives you 32, not 36.
You can't do this without being.
I heard it?
12 and 3.
12 and 3, where the positive is 12 and the negative is the 3, so the outer inner gives you the 9. So I get 2 different values for AX. What are they?
Negative 12.
Negative 12 and 3.
Negative 12 and positive 3. However, one of these is absurd.
Negative 12.
You can't have a length of negative 12, so therefore we must go with
Positive 3.
positive 3.
I actually have
So
that.
3 feet is my length for AX. Therefore, by the way, that means the whole AB is
12.
And now we can find CX and BC with ease, finish it out. You will have one like this for homework this evening.
Nice.
Reckon you can begin working on that homework. And how about you? Several people finished checking your answers. Some of you still finishing. Take just a moment longer. Questions at all on this? How many got these answers? These answers here. Questions on how I got my answers?
Nope.
Going once. Going twice. Gone. All right, for homework this evening, you are going to practice with a few of these. You also have another problem that has absolutely nothing whatsoever to do with this, just by way of review. Page 210 to 211. Pages 210 to 211. Do numbers 4 through 7 and 11. Pages 210 to 211. Do numbers 4 through 7 and 11. 11 is a random review problem, and 4 through 7 are going to give you practice with this. It is going to, as we've seen before in the problem, say, in Theorem 61, that means use the picture from Theorem 61. I know we've struggled with making that connection in the past, wanted to make sure I mention that to you. So whatever the picture from Theorem 61 is, use that picture in doing the homework. We'll see you tomorrow as we go over that, and have a wonderful rest of your day.